Thank you very much. Well, first let me thank the organizers for having invited me here. I really enjoyed the meeting, and I especially appreciated yesterday evening, and in particular this kind of spirits of these family spirits that has apparently been convening research here for a long time. I really invite the young generation to pursue in this direction and resist the tendency to have one PI, one project, and instead of that having many ideas and many PIs altogether. So this being said, let me introduce the talk. So I will discuss with you a number of granular media experiments that we have been running for the past 10 years maybe, about jamming and most recently about the Gardner transition. So of course I will tell you what all this is. So the outline of the talk will be as, ooh, this is really going fast. The outline of the talk, doing so I will respect the time. I will first introduce this Gardner transition, and then I will discuss how we can observe it in a granular system. And finally, then, depending on how much time I will have, I will discuss what are the consequences of the presence of this Gardner phase, this so-called Gardner phase, on dynamical heterogeneities at very minute scales when you are close to jamming. And eventually, I will also discuss a nonlinear mechanical response of these systems on the basis of what we have learned recently about this Gardner phase. Okay, so let's proceed by introducing rapidly what a glass is, but I think everybody here knows. But so you cool down a liquid following its equilibrium branch, and at some point, well, you don't have enough time to equilibrate, and the system falls out of equilibrium within the glass, and the temperature at which you fall off of equilibrium depends on the cooling rate of your liquids. And in the meantime, the viscosity increases dramatically when you tune this temperature at the approaches of TG. Now, in hard sphere systems, in hard sphere systems, temperature is a relevant variable, and so to study glasses in hard sphere system, instead of cooling down, what you do, you compress. So you vary the packing fraction, or you control the pressure, and now this diagram here turns into this one. So this is 1 over pressure, and you will understand rapidly why I plot 1 over pressure. This is 1 over pressure as a function of packing fraction for a hard sphere glass former. And so this is the equilibrium liquid. That is, you increase the packing fraction, the pressure increase, 1 over the pressure decrease, and this is the equilibrium branch. And then at some point, well, you don't have enough time for equilibrating, and the system falls off equilibrium in the glass. So this region here is the glass. Now, one interesting thing is that even if you are in a glass, there is still space for the particles to move, so they jiggle inside this glass, they vibrate. And you can keep compress and compress and compress, and at some point, because these are hard spheres, you will really hit a point where you cannot compress anymore. The energy would be infinite. This is what is called jamming. So jamming is this line of infinite pressure in this diagram, okay? So there are a number of properties that have been studied and discussed and analyzed about the properties of jamming, and the point is that to capture these properties following the thermodynamics within these states, it happens that you need to have a transition around here, separating the standard glass to the so-called marginal glass, and this is what is the so-called Gardner transition. So now what it is in practice. So here is a sketch of what happens in phase space. This is the mean square displacement, and this is what is in real space. So from now on, I will only talk about hard disk and hard spheres and grains, but we will see that they are quite similar. So when you are in the liquid phase, well, you are ergodic, you explore all phase space, the mean square displacement after a first ballistic branch switch off to a diffusive branch, and the particles are moving and jiggling all over, and they can explore all real space. Then you enter the normal glass. In the normal glass, the structure is frozen, which means, in essence, that you don't change neighbors anymore. The particle can jiggle in a disordered amorphous media, but they cannot escape the pseudo cage that is defined by their neighbors. The mean square displacement, because the particles cannot escape this cage, the mean square displacement plateau to a given value. And this is a value that tells you how deep you are in the value of this plateau, tells you how deep you are in the glass phase. If you go deeper, if you compress further, this plateau will, of course, go down. And this is what happens in real space. In real space, the particles are completely trapped. Now, the idea of this Gardner phase is that once you are there, the story is not over. There is a transition where, instead of being trapped in one glassy state, well, the glassy state itself branches in many sub-basins. And this happens at a very precise packing fraction, and it branches it suddenly in a cascade of multi-states. So this is the theoretical description of what the Gardner transition is, and that was first reported in spin glasses, so a very different field, actually. Now, because of this, the mean square displacement will have a very bizarre behavior, because these states, they much more look like this. You can see that the barriers will never be very, very large here. There is always a nearby metastable state because this landscape is completely fractal. Oops. Come on. It's completely fractal, and so you will be trapped for a while within one of the states, and then you will explore a little bit further within another state, and asymptotically you will reach the size of the basin in which this avalanche of states appeared at the transition. But this may take, of course, a long time. Now, in real space, it happens that these states here corresponds to collective vibrations in the system. So instead of having isolated jiggling of the particles in separate cage, the particles are still jiggling, but somehow in a collective way. And you see that there are many, many ways of having these collective vibrations, and all these ways of having these localized collective vibrations defines all these states. So this is the theoretical picture of the story. So now, is this happening in a real glass or in a model glass former is another question, and that's the one I want to discuss today. So it has been, so here again is the same diagram, so I didn't tell you in the introduction, but this diagram is actually the result of an infinite dimension calculation based on HNC theory for the liquid, and then a replica calculation for the glass phase. And they indeed obtained that the glass phase here is a first replica symmetry breaking, and that here there is an infinite replica symmetry breaking phase that appears at a certain given packing fraction. That, note, depends on the state that you follow. If you follow this state, for example, it will be here, but if you follow this state, it will be here. So this Gardner transition is specific to each glass state that you have selected when you fall out of equilibrium from your equilibrium branch here. So this, okay, is infinite dimension. So the first thing that was done was there was a simulation in a mean field glass former where they observed the same kind of diagram. And then there were simulations in 3D and 2D hard spheres where they observed, yes, this diagram, where again you have this equilibrium branch. You equilibrate your system carefully here, then you follow the states, and then you observe the Gardner line here. So I will now tell you how they observe numerically the presence of this Gardner transition, but I will first answer a question here. So the difference between stable and marginal is what I said here, is that when you are in a stable glass, you have the basin of the glass, you never escape this basin. When you're in the marginal phase, this basin is split in many sub-basins, and each of these sub-basins is not really absolutely stable, in the sense that you can escape it if you wait long enough. Okay. Any other questions? So how did they obtain this line here? So numerically what they were doing, they were trying to follow this idea that at some point the system falls, the basin split in many basins. So what is the image that you can have? Well, imagine you have the particle, so these are real pictures from a granular system that I will describe in a minute. So imagine the particle is jiggling in a cage at a certain packing fraction, and then you compress and you enter this marginal phase. When you do so, you select one of the little basins, one of the many little basins that you have once the meta basin is splitted in this hierarchy of states, and then you decompress again. You decompress again, and you are again allowed to jiggle in the meta basin. You compress again. There is no reason why you would select the same little states that appeared at the transition. So you will now jiggle into a cage that is locally at a certain distance from the first one. So if you compute the typical size of the cage, this is a very simple quantity. When you compress, it just, oops, this is really, I have two large fingers. When you compress, as I say, this is the value of the plateau in the mean square displacement, and this is just simply a decreasing function of the packing fraction. Now, the distance separating cages that occur after successive compression, when you are above the Gardner transition, when you are in the stable phase, well, you're always exploring the same cage. So this distance between the cage will essentially be the same thing as the size of this gray cage here, and that's this regime here. And then what happens is that when you go to packing fractions larger than the Gardner transition, when delta AB will somehow saturate at the size of the cage that you had at the transition and will plateau because the different cages are in this cage that was there at the transition. So somehow you have here the memory of the size of the cages at the transition. And so this is what was observed in this mean field hard sphere model, and this is what was computed in this 3D hard sphere model, when again you can see this delta AB having this plateau at a certain packing fraction while the size of the cage keeps decreasing. Notice that the scales are in logs here, so it seems to be nothing, but it's actually a matter of 1 order of magnitude. Here I'm computing things in real space. So it's really I mean, I'm not considering wave vectors really. I'm really integrating all wave vectors in some sense. Because what I'm doing here is really computing the mean square displacement of the particle. Yeah. Okay, so now let's define those quantities, or let's first introduce, yes? Yes, and I will discuss this a little bit, yeah. Okay? Okay, so let's see, so the idea is, okay, so this has been observed in simulations, but now the question is it really a robust thing? I mean, will this set up in other systems? So one particular system of interest are granular media because these are known to jam. This, as Bulbul said, this is zero temperature physics, algebra equals 0. She forgot to say that C is going to infinity. But anyhow, in these interesting systems, jamming is when you just compress your grains, and at some points, well, you cannot compress anymore if they are infinitely rigid, or you start feeling the modulus, the elastic modulus of the particles themselves. So here I want to, you see that in this problem, I want to switch on some dynamics. Otherwise, I have just this infinite pressure line where I have either zero pressure or infinite pressure, and it will be hard to make experiments where you have either zero pressure or infinite pressure. I don't know much experimental system that would resist such a jump. So the idea is to set on some dynamics again, and to do so, we shake the grains. And we shake the grains in a specific way. The grains are laying on a glass plate. The glass plate is vibrating, and the wall are fixed in the frame of the lab. So because of the friction of the grain, we somehow excite the grain everywhere in the bulk through this system of vibration. The vibration is really monodirectional and sinusoidal, so it looks very far from a good thermostat. It happens that because the system is so dense, the particles are accelerated by the vibration and immediately hit someone else. And so the vibration is typically 100 hertz, and we record the dynamics at typically, let's say, 10 hertz. And as a matter of fact, within this, the dynamics has completely scattered the vibration signal, and I will not show you the data here, but the distribution of the displacement of the grains are essentially Gaussian with fat tails, but most importantly, they are perfectly isotropic. So the system has forgotten everything about where the energy was coming from. The important point is that it's injected in the bulk and not from the wall. So at the walls, the dynamics might be slower, but in the bulk, it's homogeneous. So we have something like 8,000 or 10,000 grains in this system. We follow something like 1,500. And these grains, in this particular case, are photoelastic, as Bulbul introduced to you, so that we can either try to measure the force. This is a hard exercise, but at least we can see whether there are contacts or not. Okay, so something like 1/10 of the size of the grain. Yes, I forget to say, now to follow the dynamics, we will take picture in phase with the vibration. So we don't care about the fast oscillatory motion, and we take picture in phase with the vibration. So the grains, because of this, are allowed to explore their configurational space, and because for hard particles the problem is essentially entropic, this is actually behaving quite well like a thermal system. And we had many evidence in the past of this. Okay, so one at a time. So now we have to prepare a glass, which, as you know, is always a hard task. So the idea is, okay, I will show you here the historical protocol where we start at a rather loose packing fraction, let's say, for instance, 0.8, and we start compressing stepwise. So this is a packing fraction as a function of time. So one of the wall can move, and we can measure also the pressure at this wall. And so we increase the packing fraction stepwise, and this is a measure of the pressure or the force at this wall. And you see that here, essentially, it was not responding. And then at some point, when you make this little step, the pressure increases rapidly and then relaxes. And then you can see that it has not finished relaxing, but I don't want to wait more. This is already something like 20 minutes or half an hour. Then I make one further step, it relaxes slower. One further step, it relaxes even slower, and so on and so on. Now this is now more like 2 hours, and I'm really fed up of waiting. And also I know that probably it will take an absolutely very gigantic time to wait. And then I decompress. Now when I decompress, what is amazing is that here there is no more of this relaxation, or even very, very much slower. So we even check that if now we make up and down compression cycles, we come back to the same mean value. So here, this is in this regime that I will do all the experiments. Okay, so we record, so now, sorry? Yes, sure. I forgot to say the disks are bi-dispersed to avoid crystallization with standard ratios and standard participation fraction. Okay, so these are typical trajectories of the particles. When we are down here, that is at low pressure or low packing fraction, and the particles you see have this kind of dynamics. This is 10,000 cycles of vibrations. Note that the scales here are in diameters of the grains. So this very much moving particle is at most moving 1/2 diameter. Now when we are here, the particles hardly moved even 1/10 of a diameter. So you see that there is a huge difference here. And in all these experiments, if you look at, for example, at the Voronoi tessellation of your system at the beginning of the experiment and at the end of the experiment, they essentially overlap, which tells you that really there is no change of neighbors. And so we have really reached, from the point of view of what we wanted, a glass state. So this is my metabasin. Now I need to know that now that I know that I'm along one of these lines, one of these glassy states, I need to know where is the jamming point for this glassy state. So this is important because that will give me the range of packing fraction I have to explore. So to do this is another evidence that it was a glassy state. To do this, I use these photoelastic techniques and I compute the average number of contacts. Now because I'm shaking, and because the contacts have a finite time duration, and my camera has also a finite time exposure, even below jamming, there are always contacts. Are not zero. But clearly what happens is that when I reach jamming, the average number of contacts start to increase, and the real numbers may depend on the kind of threshold that I have to put on the gap or on the light intensity here to say there is a contact or not. It's always a bit arbitrary. But clearly, the fact that it starts increasing, fortunately, this is something that is, in terms of packing fraction, is one unique packing fraction. So for one experiment, and I insist, it's for one experiment, one glass, we have one value of the packing fraction where we know that at this point, we are really, the pressure starts probing the elasticity of the particles. It's no more the kinetic pressure that occurs in the glassy phase. Okay, this is just to give you an idea of the network of contacts, but that's not really the topic of the talk today. Sorry? The horizontal here? That's a good point. Why isn't it here? I think you will show it soon. This must be something like 0.82, and this must be something like 0.83. Yes, the range of packing fractions are very small, but this we can control easily because we have a system that is 10,000 particles, a wall that we can move with a precision up to 10 microns, and so we can tune phi very, very precisely. Okay, so now I have to describe the protocol. I've started at low packing fraction, somewhere here. I've compressed very gently my systems. I found phi j. Then I gently decompress to a certain packing fraction phi naught. The game here is not to go too far in packing to low packing fraction, otherwise you go outside your glass and you have to re-prepare the glass again. So we go to some value. We don't want to probe it too far. And then what we will do, we'll make cycle of compressions 10 times to a given target packing fraction, and we'll do this for several target packing fractions. Is that clear for everybody? So in each cycle, I will record 1,000 images. I will do this 10 times, and I will record 10 packing fractions, so that's 100,000 images that I will process systematically and so on. Okay, now what do I have to compute? Well, so I have a direct access to the position of the particles as a function of time. Below phi j, this is a specificity of granular media, you always, I think I don't know any experiment in granular media, when you're not jammed, you always have a little bit of convection setting in the system. Which, by the way, is an interesting remark, but again, it's not the topic of this talk. So to compute the things, I will always compute things in the center of mass of the neighbors. So when I take one grain, the first thing I do, I define the center of mass of the neighbor, and I use this as the local frame for this grain. So once this is done, I compute the mean square displacement of particle I within the cycle K. This is what I will call, and then I average this over all the particles. This is what I will call delta within the cycle K between time t, w plus t, well, tw and tw plus t. And I can also compute the overlap between two successive cycles. So because I follow my particles during the 100,000 images, I know what particle is even in the different cycles. So I compute the distance for this particle I between what it is in the cycle K and cycle K prime. To the square, I sum over all the particles, and this is what I previously called delta AB. This is the distance, average distance between the particles between cycle K and cycle K prime. As I said, in this phase, in the Gardner phase, there is always aging. So we have to be very careful, and also in the glass phase, because it's an experimental system, there is also aging. One is much lower than the other. We have to play with all these time scales. So in here, I will take a time window here, which is 500 cycle, which I know is smaller than my waiting time. Then I will average over a small time window 200 vibration periods to be sure that at least my averages are taken on something that is more or less steady. And I restrict the analysis to successive cycles so that I'm not sensitive to the aging in the glass phase that can also occur because I do too many cycles in the glass state. These precautions taken, these are the main results. So here you have the temporal evolution of this delta and this delta AB or delta KK prime for different packing fraction. And these packing fractions are when phi is smaller than the Gardner phase, than the Gardner transition, we will see. And you see that delta and the different delta AB, so the different curves here corresponds to different pairs of successive cycles, are essentially exploring the same space, the same values. And here, I mean, the difference is really stringent. That's why we were really confident in those experiments, in that here, when phi is larger than this phi j, now instead of this, delta has decreased 1 order of magnitude, and delta AB is still there. It's still there, it's fluctuating much less, and these are different pairs of cycles, so you can see that they are really different. So not only the delta AB are very different from delta, but also the different delta AB from one cycle to the other can be quite different themselves. So this is essentially the curve that was reported by the numericians in the 2D and 3D hardware systems or in the mean field glass former. And you see here again that we have delta that decrease, and around the value of 10⁻² in grains diameter, it splits, and delta is still decreasing as expected, while delta AB plateaus at this value. You may note here that there is a sharp difference between these curves and the one I showed you at the beginning, is that at the beginning you had a common curve that was very long, and here you had a little plateau. What I have here is a common curve that is pretty short and a long range of the plateau. Well, again, note that the packing fractions varies on very, very tiny regions. The reason for this, here I have to make a dangerous exercise. I have to come back to this. The reason for this is that you see here that if you equilibrate very well, then the stable glass phase is very large in packing fraction, and the marginal phase is small. If you equilibrate not so well, then the ratio is different. You have a small regime where you have the stable glass phase and a large region of packing fraction where you are marginal. I'm an experimentalist, so I cannot equilibrate well. Numericians are crazy about equilibrating. It's something that they are really uncomfortable not to equilibrate well enough. So these equilibrations were done around here. So that's really the reason for the difference. Okay, so let's go back to these results. So now what about aging? How much time do I have? Yes, okay. So what about aging? So these are again the numerical data obtained in the 3D hard sphere system. So these are the mean square displacements. You can see the plateau. And this is when you do the measurement not in the Gardner phase. And when you enter the Gardner phase, well, you realize that depending on the waiting time, your curves are different. So that tells you that there is aging. The curves depends on the waiting time. And what you see here is actually the fact that the particles start, they are trapped, but then they go to another cage and then to another cage. And of course, because it's completely fractal, there are an infinite number of cages, so you don't even see little plateaus. You just see a curve that crossovers gently towards the value it has at the Gardner transition around here. So we cannot really perform this, because to do this, you need to sample over many realizations. This is sampled over something like 1,000 runs. I have only one glass, and I cannot reproduce many, many glass. So what we have done, but I have different time windows. So what we have done, we have more like fixed t, and look as a function of tw if the mean square displacement is decreasing when I increase tw. And this is what you can see here. This is for a packing fraction that is not in the Gardner phase, and well, essentially it's flat. While here, you clearly see that delta decreases when you increase the waiting time. So there is indeed this aging that is expected in the Gardner phase. Okay, so now to come to the question of Shrey. What about the fluctuations of these parameters? In the theory, they are predicted to be Gaussian. And here they are not. But the theory is mean field. So we looked at the distribution of delta, both through all the cycles or within one cycle. And even when it's within one cycle, delta is not Gaussian. So we looked then, of course, at the variance of these signals, and the variance, which is some kind of a dynamical susceptibility, as a peak around the Gardner phase, which is again in contrast with the theoretical prediction. For the theoretical prediction, this chi-4 would increase, and then it would plateau at a certain value that is system size dependent. So this we don't know why. That's an interesting experimental fact. Okay, so other questions up to here. So what this tells us, it's indeed that the different fluctuations in the different cages are different. I mean, this tells us that the system is vibrating in an heterogeneous way. That's exactly the measure of the spatial heterogeneities of the vibrations, which is the essence of the Gardner phase. We see it maximal at the transition. I don't understand why then it decreases. Might be due to the softness of the particles. I don't know. But let's have a look at this. So it happens that I say, let's have a look at this. These experiments are 10 years older than the one I just presented you. So 10 years ago, we were looking at the spontaneous vibrations within a jammed system of vibrated grains. And so we were looking at the displacement, and this is typically a snapshot of the displacement of the particles magnified by a factor 50 when you integrate the displacement, say, on a time scale 100 cycle of vibration. And what you see is that it is extremely heterogeneous, but also that the correlation lengths in this system, I mean, we're not talking at all about the 2, 3, or 4 diameter scale that you have in glasses. The correlation lengths are huge. They are of the order of 10, 15 even particle diameters. And this also had a maximum at a certain packing fraction. So probably at that time, studying this, we had pointed at the existence of this transition that I just described in detail, just by exploring the correlations amongst the vibration of the system. It is important to realize that when you want to compute a correlation function associated to these vibrations, you have to define on what scale you are looking the vibrations. And so this is coming back to the question about the wave vector. Let's say that delta I is the mean square displacement of particle I between TW and TW plus T. And now I want a quantity that goes between 0 and 1, like when you do a Fourier transform. But I don't like Fourier transform because my system is not in a periodic box. And I'm not doing light scattering, so I don't see why I would do Fourier transform. So what I do, I take the exponential minus, and I divide it by a certain length scale. So this is somehow like a step function. It will go to 0 if delta I has moved more than A, and it will be 1 if delta I has moved much less than A. Then I sum this over all the particles, and that will define some kind of a dynamical structure factor between TW and TW plus T with a scale A, which would be the inverse wave vector of the dynamical structure factor usually used. Now, this quantity is fluctuating in time, and I can compute its variance, and that's the dynamical susceptibility. And you see that this is a function that depends both on the scale that I select here and on the time window, the time lag that I use to compute the displacement. What is amazing is that, so you can plot this as a function of both of them, not privileging any scale here to start with, and this is this color plot here. So this color plot is how much the fluctuations are important, and red means important, blue means 0, parameterized by the length scale on which you interrogate your system and the time scale. And you see that there is a maximum there. And this maximum, you've not selected. The system tells you what this maximum is. And now you have this A star and tau star. Tau star is of the order of 100, as I said here, but A star is 5 10 minus 3 grain diameters. So these dynamical heterogeneities are clearly not the one that you would expect in a glass where particles exchange neighbors. This is not the kind of displacement you need to escape your neighbors. These are dynamical heterogeneities at the scale of the vibrations. 10 years ago, we were looking for the dynamical heterogeneities of a glass, and it was a bit annoying, these values. Now we understand really what it was. These are the dynamical heterogeneities of the vibrations in the Gardner phase. Sorry? Okay, so that was the study of 10 years ago, but you have here, so you can either compute this maximum or you can do better. You can compute the full correlator instead of just taking the variance, which is somehow the integral of this correlator. You can compute the correlator. You can do the scaling analysis of the correlator that is plotted here, from which you extract a length scale. The square of this length scale would be somehow this maximum value, and this is its dependence with the packing fraction. Okay, so 10 minutes. So let's go a little bit further. I will skip this. 1 minute. 2 or 3 minutes. Well, it's really up to you. I mean, if there are many questions, I can stop here, or I can say a few things to trigger more questions. Okay, I go just a little bit more. So, does this has any consequence on the mechanical properties of the system? Because, you know, the particles are jiggling, escaping these little basins, etc. I mean, has this any importance? Of course, obviously, the vibrations are very peculiar. So it should have some impact on transport properties, because these have no electrons, etc. It will have no impact on the heat conductance or on the electronic conductance and so on. But clearly, the vibrations and the sound modes should be different in this system. So elasticity should be different. So we realized an experiment where we take the same system of particles, and now inside here we have an intruder, and this intruder can inflate. So let's see if this movie is going to play. So we inflate the intruder. On the right, you see the displacement of the particles. On the left, you see the intensity of this photoelastic signal in the Voronoi cells associated to the particles. The intruder has increased size, but very little, as you can see. Yeah? Okay, and we can do this at many different packing fractions. Now, when we do that, so we do this, we measure the force intensity, we compute the local stress, we take the invariance of these tensors, that is the trace of the tensor and the deviatoric part of the tensor. So for the stress, this gives us the shear strain and the shear, for the stress, this gives us the pressure and the shear stress. We can also do this for the displacement field, and that gives us the strain and the dilation. And so we have these maps for each packing fraction as a function of time and for each intruder inflation. So this is a huge amount of data. I will concentrate here only on mean values. So we could study fluctuations and so on. Let's just stay with mean values here. So I will essentially average these things radially, azimuthally, because this is supposed to be azimuthally invariant. Forget about this. This is the trick to inflate this object. And the first thing that we can note that is not trivial is that there is essentially no dilatancy. So we inflate something, and you can see that the system is so large that actually you don't compress your system, except on the first layer of grains. What is amazing is that there is pressure even if you don't compress. This is because in granular media there is something well known that is called dilatancy. If you want to shear a system, because this system is also sheared, as you can see. And so if you want to shear a system in granular media, you have to dilate. There's no way that the particles will move gently along the shear that you impose if they don't dilate. Because here I'm performing experiments at constant packing fraction, I cannot dilate, so I induce pressure. So this is a well-known phenomena. And so what we did, to make the story short, we plotted the pressure as a function of the strain and the shear stress as a function of the strain, parametric plots, and we could scale them. And the main message here is that the result is that instead of having the shear stress that goes linearly with the strain, or the pressure that goes quadratically with the strain, as expected in standard linear granular media, there is a part here that depends on the distance from jamming and on the strain, which is hence a nonlinear dependence of the elastic response of this system. So don't enter into the details of the values. The message is really that close to jamming, this system, instead of being just gently linear, has a regime where it shears soften. That is, the more you shear, the weaker it is. And this is something that is probably related to this hierarchy of basins, because you shear a little bit, and of course, as soon as you shear a little bit, because these things cannot resist really anything, the system is weaker and weaker and weaker. Okay, but this is just an hypothesis at this level of description, although there have been recently a number of theoretical work about the response of a glass sheared in the Gardner or not in the Gardner phase. The second thing before concluding is, okay, we can do another experiment, is this system yielding? Which is also an important mechanical question. So for this, we made another experiment. Now we have an intruder, and we pull with a mass. So another movie. You will see the intruder coming from the left. Below, this is just the real images, and above, it's the image when they are processed. And again, you can see the displacement of the particles. You will note that it's extremely erratic with large events and so on. So I want to conclude here, so I will not analyze this for you right now. But the message is that there are a lot of avalanches of all size and all these kind of things that are typical of marginal phases. And I will stop here and thank you for your attention.
The data on the length scale versus density. I have some. That one, no, you went too far.
The experimental one, or?
Well, it is experimental, but not this one. Keep going. C4 versus phi.
The 10 years old work.
Ah, this one.
This one you must have heard a number of times, especially you.
But, but the reinterpretation I'm hearing now, and I'm not sure about it. So I just, two questions about it. One, I mean, if what you said is the correct way to think about this, then above or rather below at lower densities, you should not see a growing length scale, right? Because there isn't one in the homogeneous glass, yeah, is what I would have expected. And secondly, when you go beyond, okay, I don't offhand know what to expect in terms of whether, as I increase the density, this distance between the different minima should increase or not. I guess it would increase, right? So why does that, coming from above, why does it diverge as I approach that threshold?
Okay, so as I said, so I mean, according, okay, if we agree, and I mean, this is really a statement, I'm not sure I agree myself, but if we state that this is also the signature of this Gardner transition, which is an open question, then the theory would predict that it grows on this side, and then it goes to infinity, and it remains infinite in the Gardner phase. That's what the theory predicts. So it's some kind of, it's critical, so that's why it grows on this side. I mean, it doesn't jump from 0 to infinity. And then it's supposed to remain infinite. This is because? Exactly, yes. So this is more like in the XY, if you want. The length scale diverges, and then in the KT phase, it's infinite forever. So for me, the question is, why does it go down? And this I don't have the answer. There might be many reasons. I mean, okay, so if you want to enter the details of the things, you see that it is really important how you prepare your system, because that will select the glass in which you are. Here I've described everything as if I had hard spheres. If you have soft sphere instead, now this line of equilibrium glasses will transform into a region of the parameter space, packing fraction temperature, where all the points that are below the glass transition curve are all equilibrated glass. And depending on the position I go from in this space towards jamming, I will hit the Gardner line in a certain way. What I'm exactly doing in this parameter space, I don't know. And I think this is part of the answer. It's probably possible to design a path such that you get something like this. But
so in the experimental setup that you have, so does it matter that whether you have smooth walls or rough walls, because you are in a regime that's well into the glass and length scales are expected to grow pretty rapidly? So does the layering play a role in the region that you probe?
So I don't know. This, what you see here, is 1/3 of the system in each direction. So we have one more box on each side before the walls. So I think the effect of the walls are screened.
And the second question that I have is got to do with, so in these experiments, now let's imagine that I were to freeze a bunch of particles. Then would you start making your delta AB narrower, and then what does it have to?
I don't know, because I've not done it, and this is not the lack of will to do it. But freezing the particles is not so easy. You know, we don't have optical tweezers there. Remember that the system is overall shaking from the bottom, so we cannot attach the particles that you would like to freeze to the bottom, because otherwise they would shear our system permanently. Yes, but this is a completely different setup. You know, vibrating this, I mean, the experiment is something that weighs half a ton altogether. So yes, we can do it, but you need to buy quite a heavy shaker. And
in the marginal glass phase, do you know how the distribution of lengths of the plateaus changes with packing fraction?
Yes, so this you had here. This you had here. So you see the width is essentially this.
That's the width of the plateau of MSD?
The width of the distribution of the plateau delta.
Okay.
So indeed, so it has this maximum here, at the values of the packing fraction where we have the feeling that we enter the phase. So probably, I mean, here we have some kind of effect that we are entering the marginal phase, but then there is something that softens everything, and the system is not as marginal as if it was pure hard spheres. But again, this is really the, I mean, as 10 years ago, when we did not understand why these heterogeneities were at such small scale, I think in experiment what is interesting is when you match the theory up to a point, and then there is a striking signal of something that is different. And this is this decrease here, and it would be interesting to further investigate that.
So, just a minute. This is regarding your drive mechanism, and what you do is a sinusoidal drive.
Yes.
If I start thinking about the particles, with velocity 0 and it starts, and the particles are stuck to the substrate. It tends to slip only when the acceleration is maximum, that's when it's reversing. So it's kind of kicks that you're giving, and how does that translate? Because it's a...
As I said, you forget all of it. That is, if you go at lower packing fraction, you see this in the trajectories, in the statistics of the displacement, and so on. But for packing fraction as large as the one explored here, you completely lose, but absolutely completely. But because you must realize, we shake typically 1/10 of a diameter, but the particles having moved 1/1000th of a diameter, it's already someone else, bounce on it, that is itself bouncing on all the others. And so after 10 cycles like this, you have completely lost the memory of the forcing. Which is not true again. If you study the dynamics of one particle on this plateau, it's something that is completely driven by the ionizer.
That splits up in the Gardner phase into a few states. Are there decent estimates on in how many states do you split up?
In my case, or? In my case, I would say that we can have an idea of this by this. By this here. So here, of course, I'm just exploring pair of successive cycles, so there would be many lines. But looking at, okay, so the distributions of the delta AB would answer us about this. But I don't have access to it. Look, I have 10 values of delta AB. How do you want me to plot a distribution?